Alright, Chapter 32, Modernization Railway High-Speed Trains. Indian Railways keep the pace with the advanced railways of the world, has modernized the railway system with a quite sudden time. Maximum permissible speed of the broad gauge section of the Indian Railways increased to 120 kilometers an hour by first introducing the Delhi Howrah route in 1969, increased the speed with the possible carrying out the extensive investigation trial of the Ranjay route with using WDM four locomotives and all cold coaches. The study was based upon the fundamental concept of the safety and comfort of the high speed depending upon the interaction with the track of the vehicle, the suspension system of the rolling stock, the very good, though even the track maintenance may be comparatively average quality, reasonable level of comfort will still be achieved to limited the extent of the track stability economically introduced in Indian railways without carrying out the major change of the track structure, simply selecting better locomotives, rolling stock, adhering to the slightly higher standard of the track maintenance. It was the reason for the Randy Express was hauled by the WD M4 locomotive, including all coiled coaches. The speed of the train, which was originally 120 kilometers an hour, has increased to 140 kilometers an hour. The Indian Railways is planning to increase to 160 kilometers an hour. Similar to the case for the meter gauge, long extent with the limits of 75 kilometers an hour has finally been overcome with the trains of the YDM locomotive. All coiled integral coach factory coaches are running at speeds up to 100 kilometers an hour since December 1997. Modernization of railways. Modernization of the railways objective of allowing the heavier trains to run safely, economically, faster speeding, improving productivity, providing the better customer service to the rail users, consisting of upgrading the track, using the better designated rolling stock, adopting superior form traction, better signaling, telecommunication arrangement, using modernization techniques and various operation rail system. Railway track is modernized by the incorporating following features in the track. Using heavier rail section, 52 kilogram meters, 60 kilogram meters, the use of the wear resistance of a heavy use section to increase the life of the rails. Use curvature switches of 1 and 16, 1 and 20 type smoother rail at the yards. Pre-stressed concrete sleepers, elastic fastenings such as the pandrol clips provide a resilience into the track, ensure smoother movement of the trains at high speed. Use long welded rails such as expansion joints to ensure smooth and fast rail journey. Modernization track methods would include the mechanized patterns, measured shovel packing in order to ensure the better tracking the geometry, facilitate the high-speed smooth travel. Track monitoring using an ampler bar, car, portable and accelerator meter, Haldi track recorder, ensure the standing of the track maintenance and plan for better maintenance of if required. Other aspects of modernization railway generally include the making of the following. User better design all coiled anti-telescopic ICF coaches, better with the spring arrangement, better braking system with safer, smoother rail travel, present universal couplers to ensure uniformity of the coupling of the coaches, introducing diesel electrical traction in order to haul heavier loads in a faster speed, introduction modern signal techniques to enable the trains to move at a higher speed without any risk, setting up a management information system for monitoring movement of freight traffic in order to avoid idle time and increase productivity, computerization train reservation system that avoid human error and provide better customer service reservations of berth, using computers and other management techniques to design and maintain railways, assess efficiently, economically, to ensure efficient human resource development, to increase the productivity, and to provide better customer service. 32.2. Effective on high-speed track. The investigation carried out in connection with the high-speed train that have revealed the increase of the speed does not necessarily result in the corresponding increase in the deformation stress in the track components, but necessarily the heavy track structure of the load deformation stress in the track components were found to be augmented as a result of the concurrent movement of the vehicles in the track, including pitching, rolling, bounce, etc. Which occurs when the track is poorly maintained. This is possible to operate the same vehicles at higher speed with the given track standards without imposing any additional loads and stress, provided the standard maintenance of the track and the vehicles are sufficiently improved to control these inhibiting movements of the vehicle which runs at high speed. The existing track structure of the Rajam route is considered to be adequate standards of speed reaching 120 to 140 kilometers an hour. To achieve the still higher speeds in order to 160 to 200 kilometers an hour, standard maintenance need to be very high, the very close to tolerance that will have to be maintained. Maintaining existing tracks, such tolerance slightly limits may be uneconomically associated with the adoption of an improved track structure, which can be maintained closer tolerance limits for the comparative low cost. The modern track structure consisting of the long welded rails with concrete sleepers, elastic fittings, ballastless tracks may be fulfilled with this requirement. This cost of the modern track may be comparatively high, but its maintenance will involve limited expenditures. Alright, vehicle performance on the track. Judging the performance of a high-speed vehicle on the track is certain that the following requirements are fulfilled. The defective location of the travel, the variation, vertical and lateral wheel load such should not reach the level where the wheels can be derailed by incident of mounting. The defect portion of the track variation, the vertical lateral wheel load should not reach the level where they can lead to the derailment as a result of distortion on the track. It should be ensured that the passengers are generally comfortable while the vehicle plies on the track and the goods are carried without any damage. D. In the case of the diesel electric locomotive, they specify that the lateral force of more than 2 meters should not normally exceed 40% of the axle load plus 2 tons. Value acceleration method of the cab location should be as far as possible limited to 3 grams both in vertical and lead direction. Beak value of 35 G's. That's gravity. May be permitted in case of the record do not indicate the significant tendency of the value to be repeated. The right index calculated for the purpose of comfort analysis based on the lateral vertical acceleration values obtained with acceleration output graphs. Right index should normally not be greater than 4. The value of 3.75 is preferred. In this case of carriage, the value of the horizontal lateral acceleration should be generally not increased beyond 3 tenths of a G. Occasionally 35 tenths of a G is permissible in the stipulated case of locomotive. The value of the ride index should not exceed 3.5. The value of 3.25 is preferred. 324 High-Speed Ground Transportation System. The High-Speed Ground Transportation System, or HSGT, is a concept developed to meet the challenges of increased demand in passenger transportation and recover their share of traffic up from the road. Other modes of the transportation detailed development of the high-speed rail systems are presented in Table 32.1 and 32.2, respectively. In the year 2001, the high-speed ground transportation system operated over a distance around 49,000 kilometers across the world, work over another 680 kilometers in progress in planning stages of various countries. 32.5 Ballastless track. The technique concept of the railway track consisting of ballast sleepers and rails and very old has stood the test of time. Such system is simply and can be rapidly extended, renewed, and dismantled. The generally problem that occurred with the ballast track is that the ballast material slowly deteriorates due to the load of traffic. Breaking of the ballast under the pressure of the exerted load causes geometrical unevenness, clogging with the ballast bed fine particles. Therefore, regular maintenance needed to restore the track alignment. The experience in Germany, other countries have been conventional track may be used for speeds up to 250 kilometers, but not beyond that. For a high-speed construction, ballastless track require the ballastless track of the railway or directly fastened to the concrete slabs using elastic fastening. The ballast track is expensive. Ballastless track is expensive, but is likely to require no maintenance during its lifetime. The success for the ballastless track is primarily based on the full advantages of its offers. Or stability, precision, and comfort. Ballastless tracks assure permanently stable. The track can be withstand with a heavy load of high-speed train traffic. Its performance characterizes the top quality, functional safety, the precise adjustment of the track up to the last millimeter while it was being assembled at the construction site. Prerequisite for the ride with comfort as well as reduction of the pressureless goes expanded appearance by the rolling stock. Long lifespan of the particular practical no maintenance with a surface life of at least 60 years with little or no requirement to service and maintenance. The ballastless track offers great availability, unmatched cost effectiveness, and high-speed operations. Flexible end-to-end effectiveness and application with a comparatively low structural height and possibility of achievement of optimal track alignment. Ballastless track technology offers a highly attractive, beneficial solution end-to-end system of technology for the main track turnout sections. Technology can be applied for the uniform basis of embankments, bridges, and tunnels. Our basis for optimal routing rail lines. The use of ballastless tracks for high-speed operation enables a more direct route with the train lines of the tighter radii, greater slope. The benefits enable the reduction of elimination of the cost of the work required for the civil engineering structure. The benefits have been led to application of ballastless track technology. Major project of the railway lines currently being undertaken in Germany, when approximately 800 kilometers of ballastless track has been installed since 1991. As well as the major projects around the world, the ballastless track has been found applications of many detailed table in 32.3. Main lines suitable for the access loads of 15 to 35 tons. Urban light rails, low vibration profiles, the go to aesthetics, suit for use for the inner city commuter rails. Turner underground tracks, poor drainage, tampering defects, and major problem with respect to conventional track. Ballastless track will center the drain, provided with low maintenance, geometrical stability. Stations use of ballast results in continuous varying rail to platform heights and dangerous passengers. Deserted areas. The following ballast due to the wind blow, sand, major problems in red. Ballastless technology resolve the problem. Bridges in an elevated system. The emission ballast allows narrower, lighter structure than would be possible with the ballast track. This has significant cost benefits. Material handling. A ballastless track is suitable for the situation when loading the materials such as coal and chemicals, either contaminants, ballast, and pollute subsoil. The ballastless track may be backfilled with rail level to allow unimpeded access across the track success for vehicles. The Indian Railway does not have any plan for providing ballastless tracks at high-speed routes because the maximum permissible speed is only 140 kilometers an hour at present. However, the ballast tracks are provided in the case of underground railways due to the under consideration. Figure 32.1 shows the cross-section of a ballastless track under the ground for underground railways. 32.1 shows the ballast track underground railways. Cement, concrete, your grooves, rubber, steel sheet, 30-degree angle. Precast rag bolt, pendrill cap, groove rubber pad, plastic tube cover the exposed threads of the bolt, and precast RCC bolts. Summary: many countries in the world developed a high-speed rail system when the trains running at the speed of more than 200 kilometers an hour. High speed of 350 kilometers an hour or more is also possible if ensured that the track system is free of adhesion. The maximum speed is achieved from so far as the Indian rails is 140 kilometers an hour. The limited speed mainly due to the old track structure, presence of the old bridge of the track, modernization, improvement of the track maintenance methods, and will enable the high-speed, smooth journeys of the Indian railways. And that concludes the reading of the railway engineering book. We're on the index now, and I don't read indexes or appendices. Railway engineering, copyrighted Oxford University Press. Indian tech,